Okay, so this is our big example for today because it really combines all of these things we want to talk about, right? Is momentum conserved? Is energy conserved? How do we talk about different collision problems, right? In terms of you go from different moments, so before and after, right? Before and after, and you might have more than one before and after, right? And so in this example, we're going to have two people who are swinging from the ceiling on harnesses, right? And they have ropes. So they start off basically with the ropes straight down, they're face to face, and they push off against one another. They have different masses. And then once they push, right, they're going to swing up. We can imagine that. And so we can see how high they swing. And we want to say, if we can see how high one of them swings, can we say how high the other one was also swung up? Okay. So these are what we call collision problems, even though in this case, it's not really a collision. It's more like an explosion, right? Because they're going apart. All right. But they share the same strategy. Right? And the first thing we have to do is just identify, right, what is before and after. And so for this, we'll actually go to our paper. Make sure the light's good. Bring this up a little bit closer, and I will also try to not move around so much to help with the video conversion. Okay. So in this problem, we really want to think about three different times. Yeah, Walter, if you could post a link, they are on the website. But if you want to post another link, that would be helpful. Thanks. Okay. All right. So here's my ceiling up here. Right. And I have really three times. One is they're hanging down with their arms touching each other. Okay. And this is before they're moving. So this is time one. So not moving. They're getting ready to push. Right? And then there's a time two just after they push. Right? So they haven't really moved yet. Right? But they're not touching each other anymore. Right? So this is just after the push. Right? And then there's sort of a time three where they've swung up. From the push, right? So they swing up to stop. So we really need to think about this as a two-step process, right? So they go from here to here, and what do we know physics-wise about what happens between those two times? And then they go from here to here, and what do we know about what happens physics-wise between those two times? Okay, so we want to break it down, and I want you to think about this, and so we're going to do this directed, right? So this is, again, before and after. There's really two befores and afters, right? Before and after, and then before and after again. Because the first thing, now that we've identified, right, the different times we're talking about, right, we need to say, are energy and momentum conserved for each of these before and afters? And we want to be able to give a reason why. And you will have to do that. You have to do that on your homework and on the recitation. And yeah, on the exam too, if you're worried about that. Okay, so I want you to think about that. We've talked about energy and momentum already over the last couple classes. So I want you to think about, what do you think for the first time? So while they're doing their push, Do they conserve energy? Do they conserve momentum? If you're still looking at the video, you should probably switch back to the slide so you can see A, B, C, D. So I can see most people have responses in. Let's just take a little more time to think about it, and then we'll discuss. Okay, just a few seconds here. All right, 3, 2, 1. All right, so the most popular answer is C, which is energy but not momentum. Next is A, which also has the energy conservation in there, and then B's close third. Okay, so almost everybody, well, not almost everybody, like 3/4 thinks energy is conserved. So why don't we talk about energy first? Does anyone want to offer a reason why you think energy is conserved? You can either raise your hand and we can let you talk, or you can just type if you want. Okay, so Emma said there's no external work. Right, so that's actually true. While they're pushing off, right, they're not, gravity and tension are still sort of up and down. We're just taking a very small instant of time. But the problem is, for energy, do we only have to think about external things, or do we have to think about internal things as well? Right, so Adam said that it transfers from potential to kinetic with no external work. So what kind of potential energy was it, though, if you think it's coming from potential? Right, and yeah, and while it's true in general that, Tyra, that energy is not lost, right? So does gravity make them push off here, though? Right? They don't change their height, right? If you're just thinking about this tiny instant between when they're still touching and when they're not. Yeah, they're using their hands, they're using their muscles, right, to provide motion. They have no kinetic energy here. And then after they have kinetic energy, right? their hands don't really act like springs. Your muscles are different, right? So your muscles ultimately get it from like chemical energy stored in your cells. And so for our class, right, we don't consider that a mechanical energy. It's something we can't keep track of. So when you have this sort of thing, this is basically an explosion, right? It's just not using, gunpowder. It's using muscle energy to do it, right? And so for us, this means that energy is really not conserved because we don't have something we can write down. We don't have a potential that we can write down that says how much energy their muscles are about to give them, right? And so really what we're going to say for us is that when they do this, the energy is not conserved. They didn't change their gravitational potential, which is the potential that we have here. They're at the same height. And they went from having no kinetic energy to having a bunch of kinetic energy, right? And so energy is not going to be conserved as they do that, right? It's appearing in our problem from somewhere. Now, we know deep down that it's coming from the fact that they have energy stored up in their body, right? But for us, we can't keep track of that. So we're going to say it's basically appearing, and so the energy is changing. The mechanical energy is changing. Okay, what about the momentum, though? Let's go back to what someone said about the external forces, right? Along the horizontal direction, which is the direction that we care about, right? Because that's where they're moving when they just start off, right? They're moving horizontally as they push. Are there any external forces acting in that direction? Okay, so we're going to do another poll. No air resistance. Let's forget air resistance. And we'll say for the tension, the ropes are vertical when they're at the close together position. During the push. So let's just say they're together and they're just going to quickly push, and they don't really move during the time that they push, right? All right, so why don't we cut that off here? So 3, 2, 1. I think no responses I'm going to take is not sure, so that's fine. Okay. All right, so no is the popular answer, right? So, and yeah, basically that's what we're looking for. There's no, right? The tension is up. That holds them against gravity, which is down, right? And in this direction, there's not some force that's really changing their momentum. External, right, to the two people. Now, they have a force on each other, right? That's giving them the kinetic energy when they push, right? But external to both of them, there's not forces going on, right? And so that means that you're going to conserve momentum here. No, there's no normal force because they're hanging from strings in the air. So, no. So, right. And so in that time, so you're going to conserve momentum here, right? So if we go back basically to our question, right? So the answer is that you do conserve momentum, but not energy. Right, and I do want to remind you people too that one little complication to this, a lot of times when we actually have explosions or crashes together, we also will just say they happen so fast, right, that even if there could be an external force, it doesn't actually change the momentum because the delta t is really small, right, if you remember back to impulse. But here we'll just say that, okay, yeah, they're still horizontal while they push, and so there's just no external force, and so you're going to definitely conserve momentum there in this direction, right? Which is the direction we care about, because in both of these pictures, they're not moving up, not trying to move up and down, so you won't have to worry about momentum in that direction. All right. Okay, let's think about now the other part. So while they swing up, right, so they've pushed off, right, they're not touching each other anymore. Right, so they go from being down here just after the push, they swing up, and they eventually come to a stop. So we're going to think about the time that somebody stops. And actually, it's good to point out, too, that they have different masses. And as we'll see, they would actually stop at different times. That's not guaranteed that they would stop at the same time. So we're going to end up thinking about, let's just think about one of the two people, right? So this one person no longer touching this other person. So you have one person starts off with some velocity, right, from the push. They're hanging from the string. They're going to swing up like a pendulum, right? So during that process, is our energy or momentum conserved? Asking about direction. So for momentum, either X or Y or both, right? Because now they really are moving in two dimensions, right? So let's think about both X and Y. And we are thinking about the whole process, right? All the way from the bottom to the top. So I guess I will just say, like, I didn't need to specify which one, because the answer for X and Y is the same. Okay, so why don't you just take another 30 seconds maybe to think about it, because there's still a lot of people haven't responded. All right, just a few more seconds. Okay, 3, 2, 1. Let's take a look. All right, so C is the winner by votes. A is also really popular. Let's see. So A and C both say energy is conserved. So let's talk about that again, right? So what's going on with the energy here? All right, they start off with some kinetic energy, right? And they swing up. And let's see, what forces are there going on, right? There's gravity, and there's the tension from the rope that's pulling them around in the circle, right? And yeah, this is just like the pendulum problem we talked about on Tuesday, right? Since they're going on that circular path, they're always moving tangent to the circle, right? And the tension's always moving, always pulling them radially to keep them turning, right? And so that means they're always perpendicular and it can't do any work, right? And so the only other force is gravity, and that's the conservative force, right? So you're converting their kinetic energy into their gravitational potential energy, right? So that's right. So energy is conserved here. That's good. All right, but what about momentum? So that's the difference between A and C, right? Well, now you're thinking about the person as your system, right? So here there are external forces. There is gravity, there is tension. And so even though gravity, even just the gravity, right, while it can conserve energy, it doesn't have to conserve momentum, right? They eventually come to a stop. So when they stop, they have no momentum anymore. And they did have momentum when they pushed off, right? Because they have a velocity, right? And just think of the simple example of throwing something up in the air, right? You throw something up in the air, you give it momentum up, right? Gravity's conserving energy the whole time because its kinetic energy gets converted into potential energy, right? But it's not conserving momentum, right? It eventually stops the thing at the top of the trajectory, and then it makes it go down. So it picks up momentum in the negative direction if it was positive before, right? And so you don't have to conserve momentum just because you conserve energy, right? And so the answer here is actually C. So that was the most popular one, right? That's good. So you have to think about momentum and energy separately. And so, yeah, so what you get here is that energy is conserved. Right, okay. So now that we've thought about that, then that tells us what equations we should be using to relate before and after, right? So here we're going to say that means that the initial momentum, which I'm going to call P1, is equal to the momentum at P2, right? Time 1, time 2. So that's the initial and the final. And here I'm going to say that K2 plus U2, so the sum of the kinetic and the potentials at 2, right, is equal to the sum of the kinetic and the potential at 3. Right, so there's a question about the momentum in X after each person goes in a different direction. So it add up to 0. They do, but it actually won't add up to 0 at all times. Because once the tension starts having that X component, right, once they start going up, the tension gets an X component and it'll act on them differently, right? And so you don't have to conserve momentum there. Right? And so yeah, so basically, because you can see, right, that they're going to lose. And really what we're going to end up doing is just thinking again about each one of these as individuals now once they've pushed off, because that'll make things easier. Because once they've pushed off, they really have nothing to do with each other anymore, right? And so in that case, clearly the momentum of just one of them is not conserved anymore, because it's coming to a stop from starting with nothing. So we're starting with something and then coming to a stop where it has 0. So this is the setup, right? This is how we want to go about thinking about problems. And this is a complicated one, right? There's multiple steps, right? But it uses all the concepts that we want to be able to use when we're doing problems. Okay, so before we go to actually figuring out how you then get to the solving part, is there any more questions about how to set this up? Okay, good. So Walter, why don't we go ahead and put a cut in here, because this is a